Hello. Oh, you're welcome. Yeah, YouTube just decided they're going to change like all the menus for their live stream. So this has been like it's been a challenge. I got off the offline with the 125 students. All right. So we're jumping in now. The one problem, one second, is that I can't figure out how to share my screen. I was going to like write right into Paint for you so I can do the problems. So I'm going old school here, and I have my clipboard. So this is going to be kind of sucky, but you'll be able to go back and watch it. I'll publish it after the live stream is over. So you can go back and look at it to your heart's content. Now, I'm just going to switch gears here and grab your folder so I can, because I see the first request that we had was for quiz 11. And so let me kind of pull that out right now. Okay, here are my quizzes. I'll go over whatever you like. We'll answer questions in the order in which they were received. Let's see. So quiz 11, number 2. All right. What I'm probably going to, in the interest of, I love all these familiar names that I'm seeing here. What I'm probably going to do in the interest of time is I'll put up solutions, double angles. No, if I'm going to give you something with double angles, then I'll give you the double angle formula. Don't waste any brain power on that. All right. So something like this. This is a L'Hopital's problem. Just kind of like throw me a bone as to where you're getting confused on this one. So what you're doing is you're showing that it's an indeterminate form, 0 over 0. You're showing that you're using L'Hopital's, and you're taking the derivative of the top. Don't forget to use chain rule in a situation like this. So here's the 8 from the derivative of 8x. And definitely want to know all your trig derivatives going in. Know your inverse trig derivatives, e to the x, ln of x. I'm going to go off on like some tangents as I'm, things as I think of things as we're going along. Then once we took the derivative of the top over the derivative of the bottom, again, I'm plugging in the 0, and there's now I have cosine of 0. Not a bad idea to memorize that secant of 0, therefore secant squared of 0 is just 1 over cosine of 0 is 1, then secant, and therefore secant squared is 1. So I have 1 over 1. Don't forget your 8 over 5. So this is just 8 over 5. Okay. Oh, requests coming in fast and furious here. All right. I'm scrolling back. So let's see. Where was the top of the list? Quiz 11, quiz 5, Thursdays, number 2. All right, and again, feel free to interject, whoever's asking me the question, if I'm not like answering your question enough. I'm just kind of right. Thursday. And again, if you're just joining me, it's not letting me share the screen. YouTube is wonderful. So question 2. All right. So what do you want to know about this one? If basically, if you have given the following. All right. So this is if you're given the graph of f prime, I think the prime here is kind of like written over with my solutions. So if you're given the graph of f prime, what you want to recognize is that your roots on this graph, in other words, the x-intercepts, are either a max or a min. And say for this one specifically, it's a min because it's going from negative to 0 to positive, right? So in other words, it's kind of like this, right? Which is what we're seeing when we're back here. This is where the min is. This one is telling us that this min is here, right? This is going as we go positive on the x-axis. We're going from positive slopes to 0 to negative slopes, which is going to make this a max. All right, so chat in if that's not answering your question. Okay. Okay. Retracted messages. Let's see. Quiz 7 Wednesday. Okay, so that was the one where you only had one. Where you only had one question. I was kind. You're welcome. Okay. Again, not really sure what the situation is with this one. Is it doesn't have the radical that I took out. I just decided to simplify the problem even further, and so you just have I can quotient rule, and again knowing your derivatives, and then just plugging in, and then you had. Wait, let me look at this. So I'm scrolling down to in the chat box just in case you have follow-up questions about this. Well, sorry, my mouse is going hog wild right now. Okay, then this was just a matter of simplification, getting a common denominator, however, whichever feels the most organic to you, and then doing whatever cancellation is appropriate. And I didn't care. As far as, but as long as you got to here where you just made this one fraction, you got some extra credit if you recognized that you had some kind of like double angle. Okay. What are we talking about? This one was I'm seeing from Noor. What if your answer is in a different form? You know, it's if you end up being, I mean, as long as it's like something in the. Yeah, it really depends on how you simplify. We'll be able to. Your recitation instructors and your lecturers we're smart people. We'll be able to, as long as we can follow your work and your work makes sense, we'll give you full credit for it. Yours has cosine and secant. You might have had a different day. This is specifically the Wednesday one. Okay, so like I said, you probably had a different day if you're looking at cosecant and secant. Okay, good. Are you saying your answer had cosecant and secant in it as opposed to sines and cosines? Because certainly that would be okay as well. Yeah, okay. Yeah, no, that's no problem. It doesn't have to be in terms of sine and cosine. I personally tend to go back there because they're easier to, if I have to evaluate. Okay, so that's what the quiz is. Question 1. I'm back to Christina. Could you go over question 1B on exam 2? And the answer is yes. Let me just get that stack out. Exam 2, question 1B. Oh, okay. I think I had one on the practice sheet that was similar to this. And just what came up before, if you're just joining us, is the question that was asked is, do you have to memorize the double angle formulas? And the answer is no. In the same way that I did this, then, and I just gave you the thing as like a hint, then as long as you know how to apply it, don't worry about memorizing them. And so I guess with this, Christina, tell me what your situation with this is. I'm scrolling down so I can see the bottom of the chat. But basically, in order to, if I want to, let me just read the question. Oh, we're finding absolute min and absolute max. When you see something like that, your mind should automatically be going to mins and maxes. I need to take the I need to take the derivative, set the derivative equal to 0, get the critical points. And in these situations, whenever you have a closed interval, you want to, and they're saying absolute min or absolute max as opposed to local, then you have to, when you find your critical points, in addition to checking the critical points, you also have to check the endpoints, because you can have a min or an absolute min or max at an endpoint on a closed interval specifically. Okay, so otherwise it was just a matter of, in order to solve this, like you could take the derivative without a problem. You just have to remember to use, I'm trying to read this backwards. You just have to, you have to remember to use chain rule here. So notice I put a 2 in front. And then in order to solve this, that's why I use this cosine of 2t to be 1 minus sine squared t, 1 minus 2 sine squared t, excuse me, in order to, I just want this all in terms of sine so that I can solve. Okay, good. Then you guys have been chatty here. Let's see, WebAssign, wait. 5, all right, so we're still, so Aiden, you're next up. 5F and H, I'm going to assume are from exam 2. Tell me otherwise if they're coming from someplace else. Different pages. No, because there's only Aiden, just tell me where 5F and H are coming from. Are they coming from one of the review sheets? If so, which one? And then I'll double back to you. Okay, what's next? All right, so now we're at WebAssign week 12, number 3 with Mimsy. Okay, WebAssigns. WebAssign week 12, number 3. All right, number 3. All right, antiderivatives. All right, I have this one. I have these written up. All right, so you're going from F prime. Oh, this is so little. I'm reading it backwards and little. If you want to get back to F, let me just take a quick peek at this. All right, because it's saying find F. So you have F double prime. So you're going to have to take the antiderivative twice. The first time I do, I put a C, and both of my initial. Wait, let's make sure I'm looking at the same one. Make sure I'm not scanning. Okay, so both of your initial conditions, that's here, both of your initial conditions are about F. So you're just going to keep the C here, and then you're going to take the antiderivative again. Wait, let me scroll down just in case you're asking questions in the moment. Okay, your problem is 7e to the t plus sine t. Yeah, it's going to be basically the same thing except for that, except for the 5. That's the only thing that's really different. So so then once you get, so then the thing to remember is that when you go from F prime back to F, this is going up a power. So this is really t to the 0. This is going to go up to t, and then you need another constant. I'm using d, and then I'm going to go one by one and plug in with the initial conditions. F of 0 is equal to 0. So that means that the e to the 0 is going to go to 1. So that makes that 5 because it's 5 times 1. And this is going to 0 out. And then we just have that's going to 0 out. This is going to, the d is just going to come down. So then I'm just going to solve. So d is equal to -5. And then I'll use the other initial condition to figure out what c is. So Mimsy asked me if you need further clarification, and if so, on which part of it. And hopefully you see how to apply it to your coefficients that you have. Where does the pi in the denominator come from? Oh, okay. Because, in fact, let me just write this. So when I plug in pi, f of pi is equal to 5e to the pi plus c pi minus 5 is equal to 0, right? Because I'm plugging in from the f of pi is equal to 0. And then I have this line. Then what I'm doing is, if I'm solving for c, first thing I'm going to do is I'm going to move the 5 over by adding. I'm going to subtract the 5e to the pi, which is going to give me, the only thing that's left on the right is c times pi. And then on the left, well, actually, technically, I'm moving it to the other side because I'm moving it with the 0. It's going to be 5 minus 5 e to the pi. I'm just using algebra for that to move this and this. And then the pi in the denominator comes from dividing out by pi to solve for c. No, I know, I don't know how to share the screen. It's so annoying. I used to be able to share the screen. Yes, exactly. After integrating everything. All right, so next, all right, so midterm 2, question 4A. Put my web assignments to the side for a moment. Yeah, I know the non-screen sharing thing is a big pain in the butt. All right, exam 2, 4A. All right, so what specifically are we looking at here? So this is oh, I'm sorry to hear that your video keeps freezing. Okay. Okay, so all right, got a couple of things in here. How many questions are on the final? There are all right, there are okay, I'll go back to the slow part. There are 2 parts to the final. There is the first part are shorter problems. There are 11 of them. And they're worth like small points. And then for part 2, I believe there are 6. There are either 5 or 6, and they're like the same length as these kinds of questions. Oh, thank you, Brian, for that, for those words of wisdom. All right. All right. So now, you got the slope, you're plugging in from you're given the point here, and again, this just goes back to your trig, ahem, and again, just knowing your trig evaluations. Cosine of 2 pi is the same thing as cosine of 0, so that's 1. So you have 5 minus. Is that 5 or is that a 2? It's a 2. All right, my reading backward skills are not happening well together. So not happening well today. So that's 2 minus 1, and then 2 plus 1. So here's your slope of 1/3, and then you're just plugging into here. Let me short it, and 6 long. The final will be cumulative. Yes, thank you. All right, scrolling back. Instead of solving this to the end, can we just plug in the points as soon as we get the derivative? Absolutely, yes. Yeah, if you think that'll be easier for you, no problem. All right, I'm scrolling back up. So question 4A, midterm 1, review sheet, exam 1, number 12. You got me jogging all over the place here. 1 second. All right, review sheet 1. Question 12. All right, what specifically is causing you to lose sleep on this one? Are there solutions for our past exams posted on Blackboard? No, because you should have gotten those from your recitation instructor. They should have gone over these in detail with you, assuming that you're going to recitation. But no, I did not post them. So this is from the review sheet. What's the situation here? Where are you getting? Right. So if we're talking, I'll just, while you're writing, while you're responding, I'll just talk about this in general, this kind of question. If you're talking about continuity, you should be looking at the individual pieces of the piecewise function within their restricted domains. You should be showing that they're continuous within the domain, right? And they all are. And you can just see my justifications for that. Then if we want f of x to be continuous everywhere, then the only potential places that they could not be continuous is where the rules change. In other words, at 2 and at 3. So the way that you can set these to be continuous is using the definition of continuity, which is to set the left and right limits equal to one another. All right. And so if you are very worried about related rates, no, they're not going to be a huge part of it. I answered your question. Excellent. Related rates and optimization, they'll be one of each. They're not going to be, they're not going to be the end all if you don't get one of them, correct. Let's see. Let me just kind of go through and see if they're just, before I go over another question, I'm just looking through the things just to see if I can answer any kind of quick questions. Do an optimization. Will we need to, all right, I'm up to Lakshta. Will we need to remember the surface area and volume formulas? No, if I'm going to give you anything other than, I'm going to expect you to know like the volume of a cylinder. I expect you to know the volume of a rectangular prism. I mean, those things are realistic. Or anything that's two-dimensional, a rectangle, a square, a circle, a triangle, you should be able to know the areas of those. But if it's something funky like a sphere or a cone, I'm going to give you those. All right, so it's really only the standard stuff that you have to know. And then the rest of this is just us talking for the question 2. I got, is that the same? Ooh, I'd have to look at that. I'm assuming that that's a squared. I'm looking at Natalie's for question number 2 on the final review. I got m to the second minus n to the second over 2. And I'm assuming that you mean, is this considered to be the same as n to the second minus m to the second over 2? And the answer is no. The only way you could have that is if you have a minus in front of it, because these are, because they're negated. It's like you factored out a negative. So just check to see where your negative is. Okay, so the rest of these are solid questions. So let me just zip back up to where I left off. Quiz. I did that one. I did those. I am up to midterm 1, 5B and C. Okay, those are going to go in that pile. This is midterm 2, midterm 1. Okay, Riemann sum, yes. Will the numbers be fit? No, no. I'm going to give you like numbers in the 6 digits because I know you don't have a calculator. Of course, the numbers are going to be fair. They'll be reasonable. Let's see, 5B and 5C. All right. For 5B, I'll try and put it close so you can see what's happening here. You have the graph of the derivative. Now, this is exactly the same as what we were talking about before with the one with the sketch from the quiz. You have to recognize that on the x-axis, you have critical points. Anything below the x-axis is going to be have a negative slope on f, slope of the tangent line. Anything above the x-axis is going to have a positive slope, or it's increasing on the graph of f. We're talking about the tangent lines. Now, as far as C, which again, we're looking at this graph, then if at x is equal to -1, which is here. All right, so that's right here. We want to know if we're increasing, decreasing, or neither. In other words, an inflection point. And what we're looking here at, if we were going to graph this, if this were f and we were going to graph f prime, then because this is decreasing, all the slopes of the tangent lines from here to here would be negative, then the f prime graph for this would have this below the x-axis, correct? All right, that means that if the f prime graph of this is technically f double prime, then if here we were below the x-axis, that would mean that it's f double prime is negative, which means it's concave down. All right, moving on. Okay, question 2B on exam 2. I'm answering Christina's question. All right. Let me know if there's something specific. I mean, I'll go over the generalities of the whole question, but if there's something specific, Christina, that you want to know about this, I'm happy to answer that. Let's see. And I see a couple of new general questions came in. I'll answer those after we look at this. All right. Now here, because we have x in the base and x in the exponent, that's why I took the ln of both sides, which enabled me to use power rule and bring the ln of x in front. And then when I go take the derivative, if this is y and these are x's, I can assume that I'm taking the derivative of with respect to x. I might have said so at the, you can assume that. Then when this is just going to be 1 over y, it's implicit differentiation. So I put the dy dx. And then for these, I'm using product rule. Right? So 1 over x times this, and then ln of x. And the derivative of this is just going to be, it's going to be 1 over sine of x times the derivative of sine of x, which is cosine of x. Then finally, if we're taking the derivative, we want dy dx, which we have here. So we have to solve. In other words, we have to multiply both sides by y to get the 1 over y to cancel out. And we know that y, we want to write y in terms of x, which is this. So when I write my final answer, everything, the power rule all stays the same. And then I rewrite y as sine of x to the ln of x. Is there any other method to use? No. When you have x in the base and x in an exponent, you have to use logarithmic differentiation. Just take the ln of both sides and just remember to do this part at the end. Okay, how do you know when to use logarithmic differentiation? Okay, this is one that, that sometimes you can use logs to make your derivative taking easier, but it's optional. But in a case like this, it's required. All right. So let me answer some of these general questions. Do we... Oh, you guys got a lot of them here. Can you please go over, tell when there is a change in concavity by looking at the graph? Yeah, I'll get to that. And do we need to memorize the formulas of sum of positive numbers, like the sum for I squared? No, you're not going to see those. How do we, I'm up to Amy's, how do we know how to put, I'm assuming that's put the inverse trig derivatives, and or we could just memorize what they are. I would just, don't worry about deriving them. I would just, there are three of them. I mean, really, there are just two of them. Memorize sine 1 over radical 1 minus x squared, and arc sine, that is, and memorize arc tangent 1 over 1 plus x squared. And then you would automatically know what cosine is. Just memorize that that's the negative version of sine. Okay, next one. Do you have to find the second derivative for optimization problems? No, you don't have to. You could, but you should justify on the exam what, if, like, when you get a critical point, you should somehow justify that the critical point is a min versus a max. And you can do that by plugging in. You can plug back into the original function, whatever your critical points are, and compare them. The biggest y value is the max. The smallest y value is the min. Sometimes it's just, I gave you, we talked about something in lecture where one of them, it was an optimization, but it was a really funky, function, and it wasn't, the critical point that we got had like radical 21 over 3, and it really wasn't feasible to plug it back in to the function to figure out which y was larger or smaller, which is why in that case it made more sense to take the second derivative, because the second derivative was a little easier to find. Then you also have the option of doing a sign chart. And again, it really, like when you have a polynomials, a sign chart or second derivative is really the way to go. Okay, so do you have to? The answer is no. But again, you should know all your tricks, so you know what your options are depending on the function. Are you going to ask us to evaluate a definite integral? I'm answering Daniel's question right now. When given a limit, using a right or left point Riemann sum, or do we have to write out the definite integral like in the sheet? I'm trying to interpret this. Give me a second. I think I know what you mean. I'm really like more interested in Riemann sum than you actually just like expanding it out like the definite integral. Can you give me an example of where we did that on a review sheet, and then I can maybe guide you from there and more completely answer your question. Let's see, how should we, number 11. All right, where did I put that pile? There's WebAssign. That's all 125. Review sheet, and I'm assuming that's from the final review sheet. Yep, answered my own question. Question 11. Oh, okay. Yeah, I would expect to know how to, like, he's asking something like this. This is easy. You saw this on a quiz. Here are your bounds, A and B. Just make the delta x dx, and anything that's x sub I, just make it x. That's all you have to do for that. I mean, that's, to me, like, you should be hoping for a question like this, not saying, oh, are you going to ask that? So I'd say, yeah, definitely know how to do that. Let's see. So where? Okay. Is that all we have to know? Do we have to know actually how to solve it using? No, something like that. I wouldn't want you to solve using Riemann sum. I wouldn't even ask you to solve that. I purposefully, when I gave you that problem, I purposefully gave you like a ridiculous thing that I don't want you to solve. Okay. When do we, wait, I'm kind of getting out of order here. 1 second. Is there a method? How do we can? Oh, okay. That's so. Fablia. How do we convert Riemann sums to definite integrals? That's what we just went over. The arc secant question from test 2. Okay, I can go over that. All right, just kind of go over this in generalities and see how we look at it. All right. A couple different ways that you could do this. You definitely wanted to do this using implicit differentiation because that was what the instruction said. And the way that I chose to do this is that I took this and I know that if it's arc secant, then let me just get to the bottom of the chat. Okay. What I did was I know that the result of this will be an angle. I called it theta, and I did that on purpose. I wanted to create an equation so I could go back to something that was familiar and easy to take easier to take the derivative of. So I just took this fact and I rewrote it in terms of secant instead of arc secant, and notice how I swapped the variables. And then when I take the derivative of this, I know the derivative of secant is secant theta tangent theta. I'm taking the derivative with respect to x, and therefore I'm going to put a d theta dx tag, implicit differentiation. Derivative of x is 1, and there's no conflict because it's the same variable. Then going back to, we don't have to know the okay. Thank you. You're answering my questions for me. Then kind of going back to here, if we're putting this together, if I'm going to take the derivative of this one statement with respect to x, then what we're being asked for, d dx of arc secant of x, is also d theta dx, which is the same thing as this tag. And then what I did here is I just solved algebraically for this. You should know the generalities of implicit differentiation and with trig formulas. And then it's just a matter of using, you want to write this in terms of x. And the way I did this was going back to this fact, because this is all one system. And I can use, then SOHCAHTOA applies to the whole system. So if I know secant of theta is equal to x, well, that's hypotenuse over adjacent. And then I use Pythagorean to figure out the other side of the triangle. Okay, so I'm zipping back up to pick up with the questions that I've kind of cherry picked from the quick general questions. Let's see. All right, so the question 2B on exam 2, can you go over how to use triangles to find the derivatives of inverse trig functions? Where give me a little more information than that. I'm kind of in the forest right now. Give me that and I'll come back to that one. Oh wow, we have a lot here. We have to know double angle. The answer is no. Number 7 on midterm 2 review sheet. That's similar to what we just did. That's So it's not a good use of your time. Let's move past that. Could you please go over question 10A, 10B, 10C in the final exam review sheet? I could do that. Fundamental theorem of calculus. You definitely want to go in knowing this. The thing that, oh, one second. The thing that you want to know about fundamental theorem of calculus, you want to train yourself, train your eye to recognize that you're taking the derivative of an integral. Derivatives and integrals are inverses of one another, and therefore it's basically they're going to cancel each other out. Now, as long as this, well, kind of zoom in closely here, as long as this is just like x or t or just some single variable, then all you need to do is get rid of the interval notation, ignore the lower bound, and just plug in this variable into the variable here. All right. Now, what makes this one different is that this is not just x, this is x squared. So I'm going to do that same thing. I'm going to plug x squared into where I have t, but I also need to multiply by the derivative of x squared, which would make this 2x. And then notice how when I moved from here to here, x squared squared, I made this x to the fourth, and I just wrote this as one fraction. What happened with c is that when you have both bounds have an x in them, then you just need to put some constant. 0 is the easiest because you're just going to ignore this constant anyway, so just put whatever there. And you're just breaking this up. So you're going from sine of x to 0, and then 0 to cosine of x, breaking it out into two separate integrals. And the format of the fundamental theorem of calculus says that the constant has to be on the bottom. The way to force that to happen is by just putting a negative in front. So I went from sine of x to 0 to negative 0 sine of x. And then I just applied fundamental theorem of calculus, and notice how I took the derivative here. So sine, derivative is cosine, derivative of cosine, negative sine. So I just changed the sign. How do we know? Perhaps you could use a. Oh, okay. So let me just answer Christine's question regarding this. As far as, so you can introduce another variable to solve and plug back in? Yes, you can. I'm down at the bottom of the chat right now. So yes, you can sometimes you can do that. If we did that in other ones, that's when you're evaluating. Here, you don't really need to evaluate, so you're not going to use a use substitution. Let me come back to examples that involve that. And then, as far as I see what your question was on second midterm, it says perhaps we can use a triangle to solve for the derivative, and that's more of like a mentality instead of using Pythagorean theorem. Like what I was trying to get you to recognize is the whole SOHCAHTOA of the x being x over 1, so you can convert into x. All right. If we're doing FTC for an integral with the variable on the bottom, you just need to negate. Yeah, you need to negate the whole integral. So that's your justification for swapping the bounds. Will you mention to use FTC? No, I would say that you, in the same way that I phrased it in the final exam review sheet, where I said, here's an integral, find the derivative of it, then you should recognize that wording, that is fundamental theorem of calculus, the derivative of the integral. Let's see. Do we need to know how to do that dx is the I wouldn't really spend a lot of time on that. I understand the concept of it, but no. All right, so I'm back up to, I'm scrolling back up in the chat. Let's see, 10A, 10B, 10C, that was fundamental theorem. Nor, can you please go over quiz 9, question 1 and 2, quiz 12, question 2, and question 7 from the midterm review sheet. Okay, so let's see what of this, hopefully we'll see what we haven't already covered. Let me get my quizzes. Oh, here they are. All right, so quiz 7 was the... Oh, Jade, did I skip over you? Question 7 on midterm 2 review sheet. I have a feeling that we already went over that, but let me just double check. If I don't go in order, I'm sunk. Yeah, I think we just, yeah, we went over that one. Okay. So I'm back up here then. Not going to knock my tea all over the place. Quiz 9. 7, 9. Questions 1 and 2. All right, so nice little related rates question and a min-max question. Okay, L'Hopital's. All right, we can go over that. We oh, actually, you know, we did, but I did it in the other review, so we definitely can do it. All right, so question 1 on quiz 9. This is just, and again, feel free to write in. I believe that, Nora, this is your question, as to what specifically you want to. Peter, I'll check in a second. What it is that you want to know about this. Basically, your. Well, I hate not being able to share the screen. If we're trying to see how fast the area is changing, then you want DADT. And then then you want to know when the area is 16. In other words, when one of the sides is 4, because I'm getting that because it's a square. All right. And then I'm getting DADT by taking the derivative of the area formula of a square. And then I have 2s ds dt, and then here's my DADT, and then I'm just plugging in. Make sure you know how to get your units. And for the second one, what happened here? We want absolute extrema, and we want absolute extrema. Therefore, we're going to take the derivative, set it equal to 0. This is a pretty straightforward quadratic to factor. You get your critical points, and then in this case, it was appropriate to, it was pretty appropriate to use a sign chart, and that's what I did to figure out where I was positive or negative, and then from there, depending on how the signs were changing, like we looked at earlier in the graph. That was telling me which one was the min and the max. And you only had to find the x values. If you needed to find the ordered pairs, you would plug the x values back into the original function. Don't plug them back into here because you just get them to be zeros. Okay. Oh, it was Fridays? Now you tell me. Let's see what happened here. All right. So I already did 2 because it's the same, it's basically the same thing. And then for this one, my battery's going low. 1 second, let me plug in. And I don't remember off the top of my head which room I assigned myself to proctor. It'll just be a surprise tomorrow for all of us. Stop, I know. All right, plugged in. All right, now for the second one, well, second one being the first one, you're finding, let's see let me just read the question so I can tell you what we're actually doing here. Yeah, I can't read it like that, I'm sorry. At what rate is the base changing when the height is? So in other words, we're looking for dB dt. We want to know how fast the base is changing with respect to time. Here are your given conditions. And so if it's a triangle, what's different about this one, instead of using the area for a square, I'm using the area for a triangle. And with this one, this is a little more challenging because before we just had s squared, which was pretty easy to take the derivative of. Here you had to use product rule. So I have dB dt, which is what we're ultimately looking for, times h plus b times dH dt. You're given dH dt, I believe, and then you're also given dA dt. So you can just plug those in after the fact. Something specific, I meant question one okay, that's still the same question. Okay, so let me know if there are follow-up questions for that, but that's just the essential. So that was nice. We actually were able to compare and contrast those two types of related rates questions. Okay. So quiz 9, questions 1 and 2, quiz 12, question 2. I assume you mean the Friday one. Oh, quiz 12, question 2. Oh, this is a nice one. All you're doing is using geometry for this. You got the answer. I was just confused as to how you took the derivative. Okay, does it make sense now that I say that it was product rule? All right, and then this one was just if the function is a constant, that means it's a horizontal line. If we're going from 9 to 12, then you're just drawing this shape. We're finding the area under the curve, which is not a curve. It's just a straight line. So therefore, you can just take the area of the rectangle to get the area under the air quotes curve. All right, next. Let's see, question 2B on exam 2. All right, for question 2B on exam 2, we already went over that. I think we got a little out of order at some point. So if you're asking for that again, if it was a different person, then just go back and watch it after the fact. Oh no, we were just past that. Let's see. Question 12 and question 7 from midterm 2 review sheet, which is here. Oh, we did that one. And then question 1, part B of the fall 2017 final. Don't worry about that. And then no, secant squared part. No. Can you go over exam 2 review sheet number 12? Oh, this one was fabulous. Wish I could put a bookmark. Yeah, it's being recorded. The live stream is being recorded. I'll release the recording of it once we're done. How much time do we have for the final? I believe 2 hours and 15 minutes. It goes from 11:15 to 1:45. So I guess 2.5 hours. Okay. Let's see. So we were talking about question 12 from the review sheet. Something specific about this. This is something that, again, you didn't have to do it like this. You could have done this. You could have done this with just, I mean, it would have been a pain because of the e to the x. But the fact that if you take the ln of both sides, this is what I was talking about before, using ln to make your life a better place. When you take the ln of both sides, the e cancels out and you just have the y, which is nice. And then here you can use your log laws once you have ln here. See how I use logarithmic power rule and product rule and quotient rule to expand this out. And now I have individual pieces that are really easy to take the derivative of. You have your ln of x, which is 1 over x. ln of sine y becomes 1 over sine y times the derivative of sine y, which is cosine of y, etc. Find the derivative. And then it was just a matter of what else happened here. Yeah, then it was just some of them had dy dx's, and then it was just you're using implicit differentiation here. I really like this question because it had a lot of different components in it. It had the logarithmic differentiation and the implicit differentiation, so you had to kind of do both. And then at the end, after you take the derivative, you're solving for dy dx. Okay, we have to know double angle formula. No, if I'm going to give you a double angle situation, I'll give you the formula. I'm kind that way. Okay, you're welcome. Let's see. Scrolling back up in sketching graphs of f prime. 1 second. Let me. Ow. I don't think I gave you any graphs. No, I would just I would know how to interpret going from f to f prime. Logarithmic antiderivatives and derivatives. I feel like I kind of already did that. If you have specific examples, then ask me. Exam 1 review packet question 7. Five, 6, 7. All right. For this to find the domain, you have to look at the individual pieces. You have 3 different things happening here. You have the square root of x, which means that x has to be greater than 0. You have the square root of 1 minus x, which means what's under here has to be greater than or equal to 0 also, which is this. And then I solve for x. And then on top of it, the denominator can't be 0. So that was that. So I took the 3 situations together and I plotted them on the number line to be able to write them in interval notation. Then we found the limit. Let me just see what I did here. Okay, so this is kind of pre-L'Hopital's. So what I did was, since I did like a plug-in and I got that the denominator was 0, I used conjugate to simplify it, and then I was able to actually do the plug-in for it. Okay. All right, so that was Madison. Questions 5, C, D, F, and H. Let's see if we've already covered those off of the final exam review sheets. 5. All right, which one? C first. All right, now here are some questions we talked earlier about changing bounds for the definite integrals, which C isn't, but some of the other ones that she's asking about are. The only really thing that you have other than the reverse power rule is substitution. So you're looking at something like this and saying, well, I can substitute u to be 2x plus 5 because that's linear. And you want to, again, train your brain to recognize that I can do this because when I take the derivative, I just have a constant. Because really the only thing, if I make u 2x plus 5, then I also need to make this du. And the way that I can do that is just by taking the derivative and then solving for dx. All right, and don't forget your plus c again because there are no bounds. For d, then again, this is a nice one. You're recognizing how you can use substitution when one piece of the function, like square root of x, if the other piece of it is its derivative. And I wrote this out for you just so you can kind of see that this is almost the derivative of the square root of x. So I made u equal to the square root of x. And then I know that du is 1 over 2 square root of x. Anything with a constant, you can always move the constant out of the way to turn it into what you want. Right? And that's what I did there. And I rewrote the bounds by using this statement because these are with respect to x. But if I plug the x's into here, I'll get my bounds in terms of u. All right, so you see I did that here. And then now I have something that's very easy to take the integral of. It's just e to the u, which is just e to the u. And then I plug in f of b minus f of a to get the final answer. These, just be careful with your exponent properties. You can't combine these because it's subtraction. You can only combine the exponents. You can only combine this into one when it's multiplication or division. Let's see. So 5C, 5D, 5F. F, again, I made this very complicated because I don't want you to know how to actually integrate that. I want you to use the properties of geometry. When you see that you have the bounds are the same, but negated, like going from -1 to 1, then what you're going to do, instead of trying to take the integral or doing substitution or anything with this, go and see if it's odd or even. You test odd or even by plugging in a negative and seeing if it comes back either to the original function, which makes it even, or the better scenario here, the easier scenario, is that it comes back to be odd, because if you have an odd function and then your areas under the curve, one's going to be positive, one's going to be negative by the nature of an odd function. An odd function has origin symmetry, right? Which means these areas, the net area is going to just be 0. So that would just be the answer. What was it? The other one was H. H is here. Let me just look at it. All right. H was a double substitution. I loved this problem, which is why I gave it to you, because I wanted to share. First pass at it, you see that you have sines and cosines, and maybe your first instinct with this would be to say, oh, well, I'll make sine the u and I'll make cosine of u the derivative. But the fact that cosine is in the denominator makes it a problem, which is why I set u to be cosine of x. And then I took its derivative, moved to the other, moved I didn't even need to move the negative to the other side. And then I did this first substitution, and now I'm going to have my -2 on the outside. And now I have this. I see I have u squared, I have u, and one is a derivative of the other, which means I did another u substitution. And I used v just for something different to do. And did the plug-in. Just be careful. Here's a place where you could potentially lose points. When you go from 1 over v and you're going backwards, you need to re-restrict the domain to be positive values of v. And then when I plug back in, what I noticed was that any u that I'm going to put in on the real number line, if I'm squaring it, it's going to be positive. And then if I add a 1 to it, it's going to stay positive. So I don't need the absolute value pipes here anymore, because this is automatically going to give 1 plus u squared is automatically going to give me something positive. All right. And then last step, I plugged in for u. I plugged back in cosine of x. All right. I'm scrolling down to see if you had any follow-up questions about that. Do you know when to change the x bounds to u bounds? And again, that's kind of going back to what we did here. Really, that's optional. You have to see which way sings to you better, because what you could do, and you could look at the lecture slides to see what the deal is. You know, because I did some of these both ways in the lecture. Nothing to say that you can't keep these as 4 over 9 and then plug back in for square root of u before you do f of b minus f of a. So again, that's a personal choice. It's going to come out to be the same answer no matter what. Let's see. Did we learn reverse chain rule? We kind of did, but we really didn't like do it formally. So with a u substitution, the reverse chain rule kind of comes naturally. Let's not put a name to it. You'll learn more about it later when you get to Calc 2. For absolute value to restrict the domain, should we do that every time we see it with ln when you're taking the integral of 1 over x? Yes, it should be ln of absolute value of x every time. Okay. Optimization. I feel like we already did that. If we didn't, then just let me know, because we're this is getting lengthy. Can you over question 4 in the final review packet? Okay. Yes. Here, this is it's kind of a surface area problem, but it's also cost. If you want to minimize your cost, it means you want to minimize your surface area, because then your materials cost less. This has a rectangular base, but they give you the relationship between the two. So at least we're cut down to 2 variables. And then we use the information that we're given because you're told that it's the volume is 20. So we can use that information in order to solve for H, or to solve H, at least in terms of W. And then it's a closed box, it's a closed container. So you need to have 2 top and bottoms, right? Your tops are 2W times W. Again, I'm trying to read this backwards. Give me a. And then you need here's your top and bottom. Here's your 2W times W. You have your short sides and your long sides, and you're going to multiply them both by 2. And then it's just a matter of simplifying this so you can take the derivative of it. At what point do I put so I simplified this. I didn't combine it with anything here because I needed to put separate costs for it. Right. So whatever the top and bottom are, they were $22 a side. Right. So I just multiplied that out to change from surface area to cost. I could just cost it out by multiplying cost by whatever the area is. And I did the same thing here for the top and bottom. Took the derivative, set it equal to 0, solved for W, however beautiful that was. And once I knew what W was, I multiplied it by 2 to get the second dimension. And then I plugged W back into here. That's what this mess is. And that gave me the third dimension. All right. We simplified. Okay, so this was just chatting. Question 6 on the final exam review sheet. Going past all the question 5s. Okay. This was related rates. Right. So you want to be able to look at the you want to be able to look at a problem and determine whether if it's asking for something as big as possible, as small as possible, then that's an optimization. You take the derivative, figure out what you're taking the derivative of, take the derivative, set it equal to 0, and solve. And determine if it's a max or a min, whether that's sign chart, second derivative, or plugging back into the original function. Something like this, how fast is something changing? That's how you know that this is a related rates question. And that's, so here, how fast is the diagonal changing? Draw the picture so you can see what's happening. You don't need to, this is going to be open-ended as far as how you're defining the variables. Here, I just, instead of using a lowercase d, I used an uppercase d for the diagonal, so it didn't conflict with my derivative symbol. And then I used the area of the triangle, because I don't need the whole square here. I just use the area of the triangle, or actually I use Pythagorean theorem because I'm just dealing with the sides in order to minimize to get the d, capital D, dt that it's asked for in the question. All right. Ask me if you want further, you want further clarification for that one. So let me just zip down here to see if you have follow-up questions. Let's see. So reverse chain rule we talked about, x to u bounds, tips to knowing when to make u, what to make u to use the u substitution. Yeah, like I said, you're looking to see if something is like a polynomial, then you're looking to see if one thing is a derivative of the other. Like if something's u squared and something else is u, then you know that the u squared, the x squared would be, if you have x squared and x as two parts of your function, then the one with the higher power is going to be u, and then the one with the just x to the first power, that would be a derivative. I talked about sine and cosine, just basically things like that. You'll see more complex ones next semester, but that's the general rule of thumb. You're looking to see if one is a derivative of the other. And like I said, with that sine and cosine, I made the cosine the u because it was in the denominator. Let's see. For the absolute value, I talked about that. You did a small part of optimization, but I am more confused in the setup. Okay. I don't understand the h equals in that fraction part. Which question number are we talking about here for that optimization? And you don't put the cost in the, oh, you got it. Okay, good. Yay. We don't put the cost in the beginning. You could. I chose not to, just because I had to do all that simplification and combining like terms, that I personally chose to do it afterwards. So I kept what I was working with at the time simple. If you put it in and you started with cost, that's absolutely fine. Okay, back to here. I'm going to answer as much as I can in the next like 10 minutes. And then my son's going to be flying in here and demanding that I take him to work. All right, I did that. Plugging in, how many questions? We got that. WebAssign 14, question 14, and question 18. Oh, good. Two things from the same assignment. These go here. WebAssigns are here. WebAssign 14. Fabulous. Oh. Now, this is 14 from WebAssign 14. This is another one of those great examples of recognizing that you have that one thing is a derivative of the other. You have arctan right here, and I wrote this out for you so you could see what the derivative is, even though it's written as one fraction. That's the fun of it, right? But if you write this out where you just have arctan, and you could keep it as tan to -1, that's fine. If that's the notation that you prefer. I wanted you to see that you have 1 over 1 plus essentially u squared. You have the derivative. So I made u arctan 7x. Now, what makes this challenging, and here's like an example of that nice reverse chain rule that we're not giving a name at this point. It just kind of happens automatically. And notice how when I went from here 49x squared, again training your eye to see here's 7, here's 49. Well, if I write it in this format, I match the 7 x's. Right, and then once I do this, if I made the whole u arctan of 7x, then with let me get this unglared, then when I take this, then I can move this over. This whole thing just becomes du. All I need to do is put the 1/7 out, and I have something that's really nice and easy to take to integrate. One second, I have to unlock the door. All right, now for 18, right, and I really like that one, question 14, by the way. For 18, what happened here? All right, again, recognizing, so we're looking at this, just sometimes like pulling things out into like breaking it out into 2 fractions maybe helps you see. See how I took the x and I wrote it as 1 over x, because I want you to see that the ln of x has a derivative of 1 over x. And here I have a nice clean 1 over x dx, which made it nice. Nice, again, to do the substitution, nice to take to integrate. And I believe, this is so little. And then what I did was when I had these have e's in them, and then when I plug them into here, well, ln of e to the whatever cleans this up nicely. So now I'm just left with the 49 and the 64. All right, so that's those two. Uh, 14, 18, do we need to know? Okay, we talked about that. The inverse trig functions, no sine, cosine, and tangent, but just know that cosine is just arc sine, arc cosine, and arc tangent, but primarily arc sine and arc tangent. We talked about that. You don't need the triangle. Oh my God, that was like an hour ago. Number 7 from the final review sheet. I feel like we already did that one. Let me look at it. They're all starting to blend together. We did not. Nice little optimization, right? Your box from a square or from a rectangle is your classic optimization problem. The things to know is how you create the box. If you make the pieces that you cut out for the sides so that you can flip up these tabs to make the box. If you make them X, then that's going to be the height of your box, which is X, and then length times width. If you start with 8 by 10, and I gave you this one just to give you an example, doing a rectangle, then if you're doing 8 and you're subtracting off X and you're subtracting off X, then the side of your box is 8 minus 2X. Same thing here. This piece from here to here is 10 minus 2X. And what I recommend before you take, if you're, we're maximizing the volume? Yeah, we're maximizing the volume. Then what I recommend is just multiply this all out so that it's easy to take. You get a polynomial. It's really easy to take the derivative of. If you just distributed x into one of them, and you just had 8x minus 5x squared times 10 minus 2x, you could take the derivative like that. You just would have to use product rule. You'd have to have the presence of mind to do that, and it wouldn't be ridiculous to do. It's, again, it's just a matter of preference. So you take the derivative, you set it equal to 0, just like in any optimization question. And what I did here was I just chose to use the second derivative test. You could have used the sign chart for this to figure out where from the, because I got the, oh yeah, the reason why this is the one. The reason why I did not use, if I got normal, like easy, like if I got x is equal to 3 and x is equal to -5 or something, I would have just probably done a sign chart. But because I don't want to, number one, I don't want to have to plug this into here. To see if it's positive or negative or min or a max. I opted not to do that. And then what I opted to do, since I had a nice polynomial, easier to take the second derivative test in this case, rather than doing a sign chart, because this, you don't really have good factors and stuff. And then the inflection point came out to be a nice even 3. And I could see here, since I have 3 plus and 3 minus, I could plot them here, figure out where I'm concave up and concave down, and then by the concavity, I can figure out which is the max and which is the min. Okay, so that I can answer the question, because both wouldn't be, both solutions are not the max. You only want to pick the one which ended up being this one, the 3 minus rad 21 over 3 was the max. Okay. Blah, blah, blah. How much about summation should we know? I feel like that's kind of too general of a question. You should be able to convert a summation into an integral. You should be able to, and then there's a question on the review sheet. Go back and watch at the beginning. We talked about that. And you should be able to understand how we use Riemann sum to, like when we're estimating the boxes, how that's really a version of summation. The sigma I squared and I cubed, you don't need to know that for the final. I think that was probably what the crux of your question was. I'm guessing. Let's see. So let me just kind of cherry pick here. L'Hopital's to resolve other indeterminate forms, such as 0 to 0, infinity to infinity, and 0 to infinity from week 11 slides. All right, let me just grab my week 11 slides. Just give me a second. Right. Okay, L'Hopital's. Using it more than once. So indeterminates. Yeah, usually what's going to happen with your, let me just kind of show you the slide. What's going to happen with your indeterminates is that you don't know what's going to happen, like with the powers, how it's going to affect the overall function when you put the base and the exponent together. So the way to handle this is taking the ln of both sides, just setting it equal to, setting whatever you're given equal to y. So you're creating an equation. Take the ln of both sides. And then the fact that you have ln here makes it so that you can get this exponent with the x with the variable in it out. You're going to use power rule to move it in front, and then you can use your indeterminate, whether you have your infinity times 0 or whatever like combination that you have of here, this indeterminate form. So use L'Hopital's to solve it, but remember, this is just the tricky part. You just have to practice this, is that because we took the ln of both sides, because we created that equation in order to justify doing that, then when we calculate this limit, we've calculated the limit of ln of y. So you need to just solve for y by taking e, by raising this both, like taking the e of both sides. Hopefully that that answered your question. All right, let's see if there are other. Number 4. I feel like, didn't we do number 4 in the final exam review sheet? We did. And question 5 on exam 2, I feel like we went through that already as well. Let me just look. Question 5, exam 2. Oh, we did not. This is just, if you lost points on this, this is a pretty straightforward related rates question. Definitely know how to do something like this, something of this level. Not a bad idea to start out with the picture. Again, like I said, I'll give you something, anything that's not like really standard, as far as anything beyond a cylinder or a rectangular prism as far as volume. I'm going to give that formula to you, so don't bother to memorize every volume under the sun. Then taking the derivative of the volume formula. A lot of people lost a lot of points on this because they didn't recognize that they needed to use product rule for this. There was no substitution to bring this down to one variable. So you just had to take them both, but you had a drdt and a dHdt, so it wasn't a problem. Let me know if you needed further information from that. Quiz 12 we looked at. I'm just kind of scanning at the end here. The cost, we talked about this. And the slide before is the same thing. Oh, well, the slide before, we're back to lecture 11. The slide before is actually totally different because they're not, well, the slide before is what you do once you take the ln of both sides for the first part of it. So if you have like a 0 times infinity, 0 times negative infinity type of thing, then you have to, what you have to do is you have to turn it into, you have to manipulate one of the pieces, because see how I have like an F and I have a G, like an F times G situation. You need to be able to take one of these and get it into the denominator using some magical arithmetic, or not arithmetic, algebraic manipulation, so that you have something over something, so you can use your standard L'Hopital's. And then for the second one here, if it's addition, it's pretty straightforward. If it's subtraction, you have to like look, you have to kind of do a fault in our stars and say you have different sizes of infinities, and you have to compare the sizes. And notice I gave you 2 examples here. If the one infinity is small, you have x squared minus x to the 4th. Well, this number, if I put 1,000,000 in here, then in here and here, then this is always going to be bigger. So this is always going to be a negative number. As x gets bigger, the result is going to get more negative. So this is going to negative infinity. But if the bigger infinity is first, then it's always going to be, you're always subtracting a smaller number, which means that it's just the result is going to keep getting bigger as the x's get bigger, which makes this go to positive infinity. Okay. I feel like we're done. So again, apologies for the screen sharing debacle. I don't know what's going on with YouTube today. I'll definitely be floating around in all the rooms at the beginning of the exam. And so I'll see all of you at some point tomorrow. Best wishes with your studying, and have a good break. Right, you're welcome.